I see 50 minutes on the display down here, which apparently means that I actually have to start now. So, the title of this presentation that was published was 55 New Features in Java SE 8. And the reason that we called it this was because it was based on a presentation that we did a little while ago, which was, funnily enough, called 55 New Features in Java SE 7. So it seemed logical to have one called 55 New Features in Java SE 8. And I've kind of subtitled this as Part 2 of Plan B. Because Plan B, if you remember, was when Oracle acquired Sun and decisions were made about what we were going to do in terms of Java SE. They decided that Java SE 7 would be split into two parts so that we could release Java SE 7 in a timely manner, and then we could push other things out to Java SE 8. So the thing is that when I came to actually put this presentation together, having submitted the title, I came up a little bit short in terms of new features. So we're actually going to call it 52 New Features of Java SE 8. But because we've only got 50 minutes, I think there's plenty of time. We'll get through all of the features, and there's still lots of new features that we can actually go through. Now, the first thing is I have to put up the standard disclaimer from Oracle, which basically says that we are not committing to deliver any of these things in any form of time, so take this with a pinch of salt in terms of what we're doing. Now, having said that, I'm going to put up another big disclaimer, because we are talking about Java SE 8 here, which is not a released standard, it's not a released product. So some of the things I'm going to talk about are down to the specification. Specification itself is not yet final, so there are still some things that may well change between now and when we release the implementation. Some of the features may well change a little bit over time before we get to the point where we have the implementation done. And if you go and download the early access versions of JDK 8 that you can do from the java.net website, you will find that some of these features are not yet implemented. So don't go and think, oh, I'm going to try out feature X, and then get disappointed because feature X doesn't actually happen to be there. So, like I say, I'll talk about all the features that we're planning for Java SE 8, and we'll see what's actually going to go into that. From a Java community process and Java specification request point of view, the umbrella JSR, which defines all of the features which are going into Java SE 8, is JSR 337. And then there are a number of component JSRs which are part of that, but define the various individual pieces, especially the big pieces of functionality that we're adding to Java SE 8. So from a new functionality side of things, there are three key JSRs. There's 308, which is about annotations on types. There's 310, which is the date and time API. And then there's the really big one, which is 335 for Lambda expressions. And as I say, we'll talk more about this as we go through. Then there are a bunch of JSRs which have been updated. They're already part of the Java SE specification, but we've made some changes. So there's things around JDBC, some JMX, Java compiler, some Streamy API for XML, other XML stuff, and some pluggable annotation processing API things. So these are the significant changes in terms of the specification, the JSRs. But in addition to that, because Java is this kind of slightly strange thing in that it's not just a programming language, it's not like C and C++, it is also the core libraries, it's also the JVM, and it is the JDK. So one of the other things that we've done more recently is introduce this idea of the JDK enhancement process, and these things called JEPs. So JEPs are a way of defining a piece of functionality or a change that we want to make which can affect any part of the JDK. So it could be related to the Java language, it could be related to the core class libraries, could be related to the JVM, could be related to tools within the JDK itself. So there's lots of different areas that the JEPs can actually affect. And what we're trying to do with this is to kind of gather together all the ideas that people have in terms of changes that they'd like to see in the JDK. So there's a fairly long roadmap that we have for this. We want to keep it going so it's sort of 3 years out, which means that that's at least 1+ releases away. Plenty of ideas that are going into that. We also want to create a format, which means that for people who want to see what's going on, it's a nice, clear, searchable, easy to find set of resources. And if you go to the website for the JEPs, there's a nice, clear list of them. You can access each of them individually, and you can see details about what specific things are being put into each new feature. Anybody can submit a JEP, so long as you are an open JDK committer. So obviously that's a reasonably high hurdle to get over. But it does mean that there is the ability for people other than people involved in JCP, other than Oracle employees, to add new features in this sense. Doesn't mean that just by submitting one that it will actually go into the final product, but you do have the opportunity to do that. And in terms of the things that we're looking at, we're not simply talking about, fairly trivial changes. We're talking about substantial pieces of work that might require significant engineering. They might require, a few months of work to actually get these things to be completed. So let's dive into the various changes that we've proposed for Java SE8. So we'll start with the language side of things. Clearly, the biggest of these is the idea of Lambda expressions. And so there's been a lot of discussion for many years now about how we should add closures or Lambda expressions to Java. And the net effect of this is that we are adding Lambda expressions to the syntax of the language. Now, don't be confused, this is not closures. We've deliberately not called them closures because it isn't a full implementation of closures. Certainly the fact that you can't capture non-final variables means that it's not a full closure in the sense that other languages implement them. What you can think of this as being is more of the ability to add an anonymous function type to Java. So here I've got a very simple example of how we might use a Lambda expression. We have an interface, the good old single abstract method type interface. And in that, I define a method, which is called isGood. That returns a Boolean and takes a parameter of integer x. If I want to have a method which uses that, I can define my method doSomething, which takes a parameter of type doStuff. And then we can call a method on that interface and say, okay, I want to call the isGood method on that parameter, and we'll get back the result. Okay, all good so far. What we're doing with Lambda expressions is allow you to provide a way of, in effect, passing a method reference to the parameter, as a parameter. And doing that in such a way that we can treat it as an anonymous type. So in the last line here, what I'm going to do is I'm going to call my method doSomething, but rather than creating an object, maybe using an anonymous inner class, which implements the interface that I've defined doStuff, I'm going to create a Lambda expression. And the Lambda expression basically says that the left-hand side of the arrow is the parameter that's being passed to the method, and the right-hand side of the arrow is the body of the method. And so what I'm saying here is that I want to check whether the answer is 42. So when I call my doSomething method and I say isGood on my variable, it's going to say, okay, is that variable equal to 42? If it is, return true, else return false. And there's a lot of details in this, which there's going to be sessions on this later on, so I won't go into it because obviously with 52 features to get through and this is only number 1, I've got some things to get through. But essentially this does add an anonymous function type. So it's a little bit different because now when you reference the variable d here, what you're referencing is an anonymous function. You're not referencing an object in the way that you would be before. So there's some interesting things that go on under the covers. Another thing that we're doing is adding extension methods to Java. what this is going to allow us to do is to say, well, we really need to be able to extend the libraries that we have in terms of the core class libraries. And we want to do that in such a way that we don't break backwards compatibility. So we need to make sure that if we add new methods to an interface, it's not suddenly going to break the fact that older compiled code doesn't contain those methods. So when the JVM tries to resolve the method and tries to call it, if it hasn't been implemented, then it's going to break and you get a runtime exception. So now we have the idea of saying, okay, I've got my interface here set, which extends collection. I've got some existing methods in that. But now, because I want to add a new method to it, in order not to break backwards compatibility, when I add the reduce method, I'm also going to provide a default implementation. So we'll be able to say that the default is to use the setReducer method in the collections utility class. And that way, if the JVM finds a jar file that has an existing set object in it, which doesn't implement the reduce method, then it will simply go and call the setReducer method in the collections class. Now, a lot of people sort of look at this and they go, ooh, multiple inheritance in Java. But it's not strictly multiple inheritance. We already have multiple inheritance of types in Java. The idea of interfaces gives you multiple inheritance of types. What we're now doing is giving you multiple inheritance of behavior as well. But what we're not doing is giving you multiple inheritance of state. So that's the important thing. There is no state associated with this because this is a static method that we're referencing. So there are no class variables that you can access from that because it's not an instance of an object. It is a static method that you're using. Annotations on Java types. Now, these have been around since Java SE 5, and they've really proved to be very, very useful, especially if you look at the way that Java EE has evolved and our move away from the whole deployment descriptor issues. So now, by using annotations, we can do a lot more in terms of making the code more readable, the whole idea of using POJOs and plain old Java objects and things like that. Now, as it stands at the moment, you can annotate a type declaration. So where you create a class, where you create a method, where you create a variable, then you can put an annotation on that. But those are the restrictions that you have on where you can actually use an annotation. In terms of Java SE 8, what we're going to do is extend that so that not only will you be able to use an annotation where a type is declared, but now you'll also be able to use it where a type is used. So this means that if you have something like a method call and you're passing parameters to that method, you'll be able to annotate the parameters as well as the definition of the method itself. So here I've got a simple example where I say, okay, I've got my method called process, and I'm passing in some set of data to that. What I can now do is provide an annotation which says that this list should not be null. When the compiler compiles your code, it will now be able to place more checks on the way your code works. So if you've got a list that you create which you don't assign anything to, and then you pass that list to this method, the compiler is going to go, hang on, that's a null. You've said it should be not null, so it'll generate an error when you try to compile your code. And it'll say, right, you've said it should be not null, you've passed a null reference, so you need to be able to change it. Obviously, you can't evaluate everything. You can't evaluate, runtime variables. So you would still potentially get a null pointer exception if you passed a null at runtime. But from the point of view of compile time, it allows the compiler to know more about what your intentions are in terms of the code, and also to be able to do more processing and more checking of the way that the thing works. The other idea behind this is to actually have pluggable type checkers, so that rather than just the way that the compiler works and the checks that the compiler can do, you can extend it in an arbitrary way, and you can say, okay, well, I want to define my own annotations, therefore I define my own checker to make sure that whatever I'm stating is going to be true actually works in terms of the code. Generalized target type inference. Now, generics. Again, going back to good old Java SE5. We had a number of things that kind of happened with generics because of the way that they were implemented. And a lot of that was to do with backwards compatibility. Because we like backwards compatibility, we don't like to break code, because as a developer, I know there's nothing worse than taking code that works, and in order to move it to a new platform, I have to change my code to make it work, because it already works. So we don't want to break backwards compatibility. But in terms of generics, that made life very hard. And we had to do some things which were, a little bit less than ideal in terms of the implementation. And one of the things that we use in generics is type inference. So the compiler will determine what the type of a parameter for a generic is at certain times. So here I've got a class list which takes a type parameter of E, and then it's got some static methods which take a different type parameter Z and then does some different things. Now if I look at this example here, where I create a new list of type string called ls, and I say that I want to use the static method in the list class to generate one of those, then the compiler can infer that correctly, because it sees that on the left-hand side, I've got a type parameter of string, therefore it's easy for me to, or the compiler, to infer that the type of the thing being returned is going to be of type string. However, if we do this little bit of code down here, we've got list.cons, which takes a head of type Z and a list of type Z tail. If I use number 42 as my head and I use list.nil as my tail, this is not going to work in terms of type inference. We get auto-boxing in terms of the number there, 42, so that gets converted to an integer object. But because of the way that type inference works within the compiler, it won't actually be able to resolve the fact that list.nil is, or should be, of type integer. What it will do is it will resolve it to list of type object, and then you get problems. So what we're doing in Java SE8 is saying, well, okay, let's extend type inference, let's make it better, make some improvements to it, so that in terms of something like this, where we're using a parameter, we can actually do type inference correctly and we don't have to worry about problems there. Similarly, if you're using a chain of method calls, at the moment you would have issues around type inference. In Java SE8, we're going to improve that, so with chains of method calls, you will also have better type inference and it will work correctly. Access to parameter names at runtime. What we can do in terms of reflection is we can look at details about the things we're using. So you can look at reflections on a class, and you can say, what is the name of that class? You can look at the methods that you have in that class, and you can say, what is the name of the method? You can say, what are the type of the parameters that are being passed to that method? But currently, you can't get the names of the parameters that are being used with that method. So that's a bit of a restriction, and we're going to extend that so that you will be able to get not just the type of the parameters being passed to the method, but also the names of them as well. Now, what that allows us to do is to tidy up some more things. It's going to make life better in terms of code readability, because by doing that, we can improve some of the way that we handle annotations. We can figure out where we got some redundant annotations based on the names of the parameters and so on. And we can also make IDEs better. So in terms of generating template code, we can do that automatically, because now we can use reflection to get more information about what's being used and then build the template code from that. There are a bunch of small things that are happening in terms of the language. So one of those is, again, related to annotations. We're going to allow you to repeat annotations. That means that if you want to use the same annotation more than once on a particular type, then you can actually do that. Single program element, multiple annotations. APT, the APT tool, that was introduced back in Java SE5 to do annotation processing. That's actually going to be removed because we're switching to the sort of full JSR 269 implementation. JSR 269 is the pluggable annotation processing API, which is really tidying up a lot of the things around that. Some other things that we're doing, there's the doc tree API, which is going to improve some of the things around Java docs. So what you'll be able to do is actually get the individual syntactic elements associated with Java docs, and until now you haven't been able to do that. So you've been able to get the overall Java doc elements, but not the individual syntactic elements within the particular Java doc comment. So that will give you an API to do that, and then we're going to build a tool on top of that called doclint. And in the same way that lint allows you to pick out the fluff from your code, this will allow you to pick out the fluff from your Java docs. And so that will look at the syntax of it, make sure that you haven't got any sort of errors in terms of the formatting of your Java doc comments and so on. Again, related to Java docs, we're adding an API support so that you've got the javax.tools. That way you'll be able to run the Java doc functionality, the Java doc processing, not just from the command line, but in the same way that you can call the compiler through an API, you'll now be able to call the Java doc tools through an API. Again, that helps with the idea of things like IDEs, because they can then interact with that programmatically rather than having to execute it through a command line interface. From the core libraries point of view, what are we doing? Well, first of those is to make use of the fact that we have Lambda expressions in Java SE8. Now, it's all well and good for us to add Lambda expressions to the language, but if we didn't then use them ourselves in terms of the class libraries, it would be, well, you know, not the most ideal use of Lambdas. It is no small task, because if you look at Java SE7, there's just over 4,000 classes in the core libraries. And that's obviously very good for us, because it means there's lots of APIs to choose from. But it also means for us, as the people doing the work in terms of implementing Lambda expressions in all of these, it's a lot of work to actually have to do. What it's going to allow us to do, though, is to modernize the libraries. We'll be able to simplify a lot of things, and we'll also be able to take advantage of performance improvements. One of the key things with the way that the Lambda expressions are implemented is that we're not just doing a syntactic de-sugar of a Lambda expression into an anonymous inner class. That's one approach we could have taken, but it's not what we're doing. So the way that we've done that is to say, okay, let's use the invoke dynamic bytecode that was introduced in Java SE7. And that way, rather than choosing the way that we're going to implement the Lambda expressions at compile time, we can use invoke dynamic to say, we'll decide how we're going to implement the Lambda expression at runtime. And that way we could effectively de-sugar it into an anonymous inner class, or we can use method handles, or we can use static methods, different approaches depending on how we want to do it. And the most important thing about that is by using these in the general class libraries, we can get a significant improvement in performance because we're going through the invoke dynamic bytecode. The other thing is that we can then also show people that this is a sort of reference implementation, best practices for the use of the extension methods, because I mentioned extension methods. They're not just for us to use in the class libraries. You're free to use them in your libraries as well. A few things around concurrency and updates to that. Certainly one of the ideas of introducing Lambda expressions was to make life easier for writing parallel code. And there are other things that we're doing as well. One of these is the idea of a scalable update variable. So what this says is that if you have a particular variable that you're using in your code where you've got a number of different threads all trying to update it at the same time, that can be a performance issue because of the fact that lots of threads means you have to have locking on the variable, you've got contention, you've got blocking, you've got waiting, all those sorts of things. So what we do with the idea of a scalable update variable is to say, well, if you've got, let's say, 3 threads updating a variable, we'll actually generate 3 different instances of the variable internally. And then each thread can update that variable independently. And that way there's no locking, there's no contention, and you get very good performance. Now, of course, the first thing that most people go was, okay, if you've got 3 instances of the variable, when you want to read it, what do you read? Because that would be wrong. So the answer to that is quite simple. When you want to read the variable, then the system has to figure out, the JVM has to figure out, okay, what is the actual value of that? But the idea is that this is going to be used where you have a variable that is being written to a lot, but read to infrequently. So clearly, if you're going to be reading to it and writing to it, pretty much the same, it wouldn't give you any improvement in performance. By doing this in a way that it's a frequent write, infrequent read, you can avoid all of the locking when you need to do the writes, and you only have to lock everything when you need to do the read, and you need to calculate what the value is. So there's what's called a double adder and a double accumulator. A double adder, as you would expect, is where you can add things to that variable. A double accumulator is where you can specify an anonymous function, as in a Lambda expression, to define what the accumulator is actually going to do. So what function you want it to perform when it's being updated. So that's one interesting thing that we're doing. Concurrent hash map, there's a couple of minor updates happening with that in terms of scanning support and the way that we compute the keys that are used for the hash map. And we're also improving the fork join pool implementation. And what we're doing here is using what's called a completion-based design. And the idea here is that if you've got lots of threads all working in your fork join pool, what can sometimes happen is that you've got one thread which is kind of being used and other threads need to provide the results to. So if the first thread is doing something which prevents the other threads from allowing it to add or return the results and actually carry on, you get a number of threads that can be blocked, and it reduces the efficiency of the system. So what the completion-based idea says is, okay, well, when a thread needs to have the first thread do something, what it basically does is rather than blocking and waiting for that thread to be available, it simply says, okay, here's what I want you to do. When you finish doing what you're going to do, tack this bit on the end. So it gives the work to the other thread. That way the thread that would be waiting can then be put back into the pool and can carry on doing some work. So it's really just shifting the work from a number of different threads to say, okay, we need to make this sequential. Rather than doing it with multiple threads, we just add the work on the bottom of the list of things that the one thread has to do. Bulk data operations for collections. Again, this is using Lambda expressions. It's using the idea of the extension methods in interfaces. What we're really doing is sort of adding some of the same functionality that's already available in things like .NET. So if you've seen things like LINQ, then it's similar kind of idea to filter, map, reduce. Very common approach, very common pattern to how we can do bulk operations. And so the way that a lot of this is being designed is through the use of the stream iterator. So there's a new class that's being used which will allow you to link together methods in collections so that when you pass the results from one method to another in a chain, rather than having to wait until your method has completed all of its work and then passing that result set to the next piece of the chain, you can actually do lazy evaluation, or you can do parallel evaluation. So it hides the complexity underneath. So we can say, okay, in the library code, we'll simply implement some filter method, some reduce method, some map method, even some parallel method. And the library code will handle how all of that actual magic takes place. A lot of it will build on top of the fork join framework so that we can take things that can be split up into parallel tasks and have those execute on separate threads. But again, by using the framework, we're hiding the complexity from you, the developer. So it makes life a lot easier for you. Similar to that is the idea of parallel array sorting as a more specific type of operation and making that parallel. So what we're going to do is add some methods to the java.util.arrays method class, and what that's going to do is say, okay, parallel sort, and there'll be a number of different signatures based on different primitive types. And what we're trying to do here is use the parallel array implementation that Doug Lee created and implement that so that you can take an array and you can sort it in parallel. And what we're trying to do here is to say, okay, if you've got something like, well, based on a dual core system with an appropriate size set of data, we're looking at least a 30% improvement in performance in terms of sorting that kind of array. One thing that is of issue, I suppose, there is the fact that you need a working set which is the same size as your array. So if you've got a very big array and you want to do a sort on it, you're going to need to make sure you've got enough memory to hold the working set in memory. How parallel is it? Well, it's n. Yes, I mean 2 for a dual-core system, n for an n-core system, yes. Date and time APIs. This is JSR 3.10. What this is doing is really trying to address some of the limitations that we have in the existing date and time way of doing things. Date and time is one of those things that's really kind of complicated because, you know, you might think, well, you know, there's 7 days in a week, there's 24 hours in a day, there's 60 minutes in an hour. That's simple, isn't it? It's easy. Well, yeah, once you get into calendars and, you know, whether we're dealing with the Mayan calendar or whether we're dealing with the, you know, the Gregorian calendar or whatever, these kinds of things get more complicated. And so what we're trying to do with this is to simplify a whole lot of things and also improve performance. So there's various concepts that are being supported here. So there's the idea of what's called a partial. So that would be where you say something like March the 20th, but you don't say which year it is. So it's not a definitive point in time. It's a, you know, it's a date in a year, but not a specific year. We've also got the idea of a duration, where we're talking about a number of nanoseconds since the epoch. We've got the idea of a period, which is a period of time since the epoch being January the 1st, 1970, for the Unix files amongst you. And also have the idea of an interval, which is the period of time between 2 points in time. And then there's other things that we're defining, like date and time and instant, various concepts that are used in terms of defining the higher level structures. There's also support for different calendaring systems, as I said. So primarily it's based on, you know, our calendar system, the Gregorian calendar. There's also support for other calendar systems that are very common. So if you go to like the Islamic calendar, that's, I believe, supported. There's various standards that we are implementing. So ISO 8601, CLDR, BCP 47, all those types of things. And like I say, based on UTC and things like that. One of the key things there is moving away from the idea of having a point in time which is stored as not just the number of nanoseconds since the epoch, but also as details like what year it is, what day it is, and so on. So now the idea is to simply store it as the number of nanoseconds, and then when you need to know what day it is, that's calculated on demand, and that can actually improve efficiency. JDBC, some updates there. There's various little bits and pieces going on there. There's some generic set and update methods for things like result set, prepare statement, and callable statement. Again, implementing various things around JSR 3.10 so that we can use the new date and time APIs in respect of JDBC. Reference cursor support for callable statements so that you can get result sets and various store procedure type things like that. There's a get index info has been extended to support columns of cardinality and pages. Must admit my database skills, despite the fact that I work for Oracle, are not that great, so that's what we're doing. Also database metadata, extending that a little bit to give you a method which will give you the maximum logical size of a LOB, large object. Base64, encoding and decoding. Now, it's one of those things that it's quite strange to think that we haven't had a standard API to do this. 4,000 classes, and we don't have a standard way of doing Base64 encoding. So up until now, you've had to use the sort of hidden classes, the sun.misc.base64 encoder and in decoder. Now there's going to be a standard util API which says, okay, Base64 encoder, Base64 decoder, and then you've got the usual methods like encode, decode, encode to string, wrap, and so on. Some small things that are going on in terms of changes around the core libraries. The Java x.lang.model, this is used in annotation processing. And what we're doing there is, again, we're going to tie this into some of the reflection stuff that I talked about earlier. And what that enables us to do is to say, well, rather than doing annotation processing only at compile time, we'll now be able to do it at runtime as well. So by using the reflection APIs, tying that into the model API, you'll actually be able to look at annotations and get information about that at runtime as well. A few things about character sets. Most of this is really just sort of improvements in efficiency, a little bit of improvement in terms of like size, just making things smaller, stuff like that, performance of encoding and decoding, reducing the amount of memory usage in the core libraries. So we've been looking at various ways that we can just, polish our libraries, I think is what I would say. So reducing object size that we have in there, reducing the sort of internal table size by default, various other things that we can do just to really tweak things to improve efficiency. Looking at internationalization and what we're doing around supporting languages other than English. So one of those is locale data packing. So there is a locale data markup language that you can use to generate the locale data files, supporting that. There's also the common locale data repository, which we will be supporting as part of the Unicode effort. And then also just getting more locale information from the platform that you're running on. So a lot of operating systems have quite complex locale setups that you can get access to. And so we're just going to make it easier for you to see what a particular user's settings are in terms of their locale information. BCP 47, locale mapping. This is the best current practice, number 47, for locale mapping. I think that's best current practice in 47 in general, not specifically to locale mapping. Again, this is really looking at how we can take the ideas of getting more information from the underlying operating system and saying, right, how do you want to use that to make the user's interface specific to their settings? So there's things like having a range of languages provided, so we'll have a collection of those. We'll also have a language priority. So if you want to start off with French as your priority number 1, then go to German, then go to Spanish or whatever, then you can do that as a list. And then in terms of the locale class, we're adding some methods to say, okay, filter the results that we need in a basic form or filter in an extended form, based on other criteria that we need for the user's locale, and also looking up the general things that user needs. So again, a lot of stuff around locales and making sure that the user can get the settings that they actually want. Unicode 6.2, this is really just a sort of point revision in terms of including different things. So there's we updated to Unicode 6.1 and now we're going to Unicode 6.2. An extra 700 characters to choose from in the Unicode thing. So should you wish to do like Sanskrit, then that's probably supported there and stuff like that. And also the very important new Turkish currency symbol, which we will be supporting. Looking at security. So obviously this is a fairly hot topic, shall we say. I'm not going to say any more on that, but things that we are doing around changes in terms of the Java environment. One of them is a more configurable secure random number generator. And so there is this class called secure random. Linux has this interesting sort of way of generating random numbers. And so there is a /dev/random device, which is what we use as a seed for generating random numbers. And it has a thing called a system entropy pool, which is like how much disturbance or whatever there is in the system. And it uses that to generate the random numbers. And sometimes if you're taking random numbers or seeds for random numbers very, very quickly, the system entropy pool can get too small. And so it stalls before enough entropy is generated within the system to replenish the pool. So we're looking at that in terms of improving it, seeing if there's ways that we can do that in a better way. Again, that's a work in progress, that particular one. Enhanced certificate revocation checking API. At the moment, if you look at the way that the java.security.cert API works, it's kind of an all or nothing, which means that if it can't contact the server, then it becomes a fatal error. And what we want to do there is to introduce a couple of new classes, revocation checker, revocation parameters. And what that's going to do is the revocation checker will evaluate the status of a certificate revocation based on the revocation parameters object, which encapsulates the revocation request properties. Yes, I got that right. Hope I got that right. A few other small items. Limited do privilege. So this is a new method that we're adding in terms of being able to execute things like a Lambda expression with the privileges that you have. So there's ways of tying that in. Few other things. There's various 3-letter and 4-letter acronyms. So there's the NSA Suite B cryptographic algorithms and the AEAD, which is the authenticated encryption with associated data. Cipher suite support. So both of these are really sort of mandated by the US government and various banking institutions, so we need to support those. There is the secure hash algorithm, SHA, version 224 message digests. We need that because apparently there's a flaw in SHA-1. And then we're also looking at how to leverage instructions for cryptography, basically pushing out some of the work onto the processor, so we don't do it in software, we actually do it with hardware acceleration. More small changes around security. So there's things like better interoperability with some of the Microsoft side of things, Microsoft services for Unix. There's a minor update in terms of transport level security, server name indication. So better things for virtual hosting, virtual machine infrastructure, and so on. Then you've got public key cryptography standard, PKCS, number 11. So that's a new provider there. Again, what that's going to do is improve performance because we're making use of the native operating system capabilities. Stronger algorithms around password-based encryption. Both researchers and hackers move on, so we need to improve the way that we're doing things there. And then a bit of an overhaul around key stores. So there's the Java key store, there's the Java cryptography extensions key store, and then the public key cryptography standard key store. So what we're going to do there is just tidy up a few things around the way that those are used. How am I doing for time? 8 minutes. Okay. The platform. One of the things we're going to do is provide some support for launching JavaFX applications. So if you're using those, it's really just sort of simplifying the way that JavaFX applications get launched from the command line, so you don't necessarily have to explicitly state the jar file for JavaFX on the command line. Compact profiles, because the project Jigsaw has been pushed out in Java SE 9, full modularity is now in Java SE 9, we needed something that would enable us to subset the class libraries. And this is the idea that we've come up with. So we're having a set of compact profiles, which, like I say, are effectively subsets of the class libraries. Compact profile 1 is only 10 megabytes, so that's really just sort of logging the class loader, the security manager, and so on. Then you've got compact profile 2, 17 megabytes, compact profile 3, 24 megabytes, and the full JRE, about 140 megabytes. So, I'm not sure if that's right. Okay. Better check that. It looks rather large to me. I think it's less than that. Some other things we're doing in terms of preparing for modularization. So looking at things that we can do to help us when we do get to Jigsaw in Java SE 9. So there's a few class loader assumptions that we need to tidy up. Some of the things like JAX-P don't use the standard service loader class in order to provide a service provider interface. So you can plug in your processor that way. So we're going to make sure that all of the places where you have a service provider interface, where you can plug in things underneath, will use the service loader interface to give us a nice standard way of doing things. Some analysis of application code dependencies. That's a lot of work that's already happened. They're also deprecating some APIs. If you look at things like java.util.logging.logmanager.add property change listener, things like that, you find there's some really weird dependencies. So we wanted to have the minimal subset have logging enabled in it, but you find that logging depends on a class which then in itself depends on AWT. So in order to have logging, in theory, you have to have AWT, which is kind of bizarre. So we're going to deprecate some of the APIs in order to solve some of those problems. Also going to look at the way that some of the things work in terms of Java Home. So whether you have an explicit path for some of the command line options or whether you use a relative path, again, just to make life easier. Stripped implementations. This is quite an interesting idea because what it now says is that we've always stuck to the write once, run anywhere idea, where you have to use you have to have the full JRE in order to qualify as being Java, and this has caused many problems for various things in the past. What we're now saying is that you don't have to do that anymore. You can actually strip down the JRE and only provide the class libraries that you actually want. But that doesn't break write once, run anywhere, because it can only be used in the situation where you have a bundled JRE with an application, and that JRE may only be used with that application. So it will have all of the class libraries the application itself requires, but you can't then try and run another application on that JRE which might have different requirements and therefore break. So it will not break write once, run anywhere, but it will make it nicer for people deploying applications because they can make them a lot smaller. The virtual machine, a few changes here. This is basically we're looking at just improving performance and efficiency and so on. So there's things like the way that we implement method handles. Currently that's done with a bunch of assembly code and is platform specific. Some of that we're going to rewrite in Java to make it more portable. We actually think we can make it more efficient that way, and we can switch to like the full or a better reference implementation of Invoke Dynamic doing that. Project Nashorn was a rewrite of the JavaScript engine that we had. So we had the Rhino JavaScript engine before. This is really just replacement for that so that we get better performance. It's still using the existing javax.script API, supports the fairly recent ECMAScript 262 edition 5.1 language specification. There's actually a command line tool that will allow you to run JavaScript from the JVM, and some internationalization of messages and documentation. Some rarely used garbage collection combinations are being retired. So I found this was quite interesting. So the def new plus CMS is being retired. The parallel new plus serial old is being retired, which makes sense. Incremental CMS, I was very surprised to see that. Anybody use incremental CMS? Okay, well, one person. Okay, that might explain why they're going to retire it. What we're saying here is that there's a large, I'll talk to you later, large effort in terms of testing for little return because very few people use these. It is going to be deprecated. We're not going to just simply remove them straight away, so we will give people a chance to figure out what's going on. Remove the permanent generation permanently. This is really related to the work that we've been doing in terms of combining JRocket and Hotspot. JRocket didn't have a permanent generation, so we decided that was a nice idea. We'd do away with it. All of the things that were in the permanent generation, so your intern strings, your class metadata, and class static variables, are being shifted to obviously somewhere else. So they now go into either the general heap or they go into native memory. Fence intrinsics, this is a fairly low-level thing, and for most developers you won't actually see any of this, but it's very useful from the point of view of library code. So for people who are writing library code, there is this lovely class, the sun.misc.unsafe class. I always like things like unsafe, like don't use it, ooh. But it's actually to do with memory access. And so we've introduced 3 new methods there, which is load fence, store fence, and ring fence. And essentially it's to prevent reordering of instructions, which could well happen in terms of the way that both the compiler and the runtime system work. So if you use load fence, it basically prevents load instructions from being reordered between or before the instruction is called and load and save instructions after the instruction is called. Same thing for store. Ring fence basically says load and store instructions have to be done in the sequence that they're specified. And again, like I say, it's something that's internal. We may expose it as part of the concurrency libraries in future. That's something that might happen. I've got 1 minute. Yeah, I've got 1 minute left, so I'm going to keep going. JVM compiler control. So this is about adaptive compilers. So again, this gives you API or programmatic control over the way that the compilers work. So you've got options that you can put together as a compiler directive, and then you can use a method matcher to say, okay, these are the directives that I want to use for a specific method, and that will allow the compiler to use different approaches for different methods based on your requirements. Some small things, enhanced verification errors, so like bytecode verifier will give you better messages, reduced cache contention on specified fields by padding things so they don't use the same cache line, reduced class metadata footprint, so we're using some of the Java ME side of things and what we did in the JVM there, and also contended locking, some of the work that Oracle Labs have done to improve that, and also creating a small JVM. This comes back to the profiles, compact profiles thing. We want a JVM, libjvm.so, which is less than 3 megabytes in size. And I've got 2 slides left, so I'm going to finish. With the JDK, we're also tidying up some of the build things. So there's going to be an autoconf-based build system, so you can just do /configure in the same way you can with many other things, and improve the build speed by using multiple cores, or all the cores that are available, doing various other things like tracking packages, automatically generating header files, and just cleaning up class and header files that are no longer needed. So to conclude, Java SE will add plenty of new features and remove a few. It's going to cover language, it's going to cover libraries, it's going to cover the JVM. And we will continue to evolve. So if you want more information, jdk.java.net, jdk8.java.net, jcp.org, and the JEPs are at openjdk.java.net/JEPs. And with that, thank you very much. I don't know if I have time for questions, but I mean... So the question was about smartphones? Okay. Yeah. Well, so the question was, if we're saying write once, run anywhere, how does that apply to smartphones? Well, obviously, you know, smartphones are a place where Java is not necessarily strongly represented as a core development platform. But what we have done is proof of concept where you can actually implement a JVM on both iOS and Android and have your applications run as part of that. So we recently open sourced this as part of the Java FX side of things. So we're not promoting it as an Oracle-sponsored technology, but from an open source perspective, it is available. So we're still saying write once, run anywhere. And our big push at the moment is much more on embedded devices. So we're looking at the Internet of Things, and embedded devices as really, you know, device to data center is the way we describe it. So we're focusing more on those types of things rather than necessarily on the smartphone side of things, for obvious reasons. Okay, thank you very much.